Awesome. Thank you for having us. So I'm really excited to talk today about how to manage your data like code and what that means. If I can get the clicker to work. There we go. Awesome. When we say manage data like code, what we mean is we want to bring the best practices from software engineering to your data set lifecycle management. So everything that we've learned about monitoring and managing complex systems of software, we want to try to apply those same principles to your data sets. And before I get into that, I just want to talk for a minute about my background. I've been working as a back-end and distributed systems engineer in the Bay Area for a little over a decade. I've worked at a lot of these large companies, some of them that I don't need to name in this venue. And the thing that's really connected my career and the projects that I've really been passionate about are working on large-scale data problems. And so that started out with simple things like writing ETLs for managing data warehouses and transforming that data, to running machine learning pipelines at Google, doing everything from gathering data sets to feature extraction, model training, and serving. And then at Sidewalk, I spent a long time working on distributed simulation environments. And the thing that connects all these projects is, one, there's a scale of a large amount of data, and two, there's a diversity and complexity that comes with that data. So for instance, in our machine learning applications, we were pulling features in from all over the company at Google. It was a very heterogeneous data set, and managing the different data schemas and types became a very important problem. Okay, so these are the types of problems that I have encountered everywhere I've been, and I'm sure that most of the people in this room have encountered similar subsets of these problems. So when you're running a large data system, you'll have issues with incorrect and missing data. You'll have type issues. You'll have schema mismatch issues. You'll have failed pipelines, buggy pipelines, delayed pipelines, and all of those will ripple through your systems and impact other pipelines downstream. You'll have inconsistent formats and handling of your date times, your time zones, your units of measurements. And then in the machine learning space, you have a new set of problems you have to worry about. If you have an ensemble model, for instance, like a stacked machine learning model that built on 4 pre-existing models, if you've trained those models on differing data sets, then your ensemble model will introduce its own set of inaccuracies and failures. You have to worry about training serving skew, which is broadly anytime there's a difference between your model when you trained it, when you served it. For instance, if you introduce a new feature set, or if you change your hyperparameters, you train a new model, but the code that's serving your model hasn't been updated, it's going to produce garbage features, and your data quality is going to regress. And then the last issue I want to talk about is data quality regressions that occur over time. For instance, if you build a pipeline, you build a machine learning model, it's performing well for a few months, you let it run on its own, a couple months later you come back, the quality's gone very poorly. Now you want to be able to debug what was the input data that caused that initial problem, and that's actually a fairly tricky thing to do when you have a lot of data. Okay, there we go. So there's a growing understanding of a lot of these issues. There's been a lot of papers that have come out of industry and been published about this. This is kind of the canonical slide that everyone should look at before they go to build a real-world machine learning system. And this was from a paper called Hidden Technical Debt in Machine Learning. It's published out of Google in 2015. And the key takeaway from this slide is that when you're building a machine learning system, the actual amount of work that goes into your machine learning code is a very, very small part of that system. If you want to build a real-world production system, you have to worry about all of these components. And in this diagram, the components are scaled towards the cost and complexity of those subsystems. So you're actually going to spend most of your time dealing with data verification, data collection, feature extraction, configuration management. And so what we really care about is what can we do, what kind of frameworks, what kind of practices can we build around this part of the system so that we can remove those problems and you can focus on the core ML work that you care about. There we go. So there's this great quote from Scully, and he had this observation that increasingly, as we have more and more machine learning systems, the behavior and control of those systems is dictated by data and not code. And so all the best practices we had about testing for code changes, testing, doing integration tests on code, we should really be applying those same ideas and practices to our data sets. So where does Quilt fit into this? I found throughout my career, as I was working at these different companies, everywhere I went, people were building very similar tools to manage their experimentation, to manage their data, to manage their consistency and their lineage. They were all building these in-house. If you were really lucky and worked at a giant company, there might be a dozen tools that were being built to do all the same thing. And so when I met Kevin, who's the CEO of Quilt, he was telling me about data packages and about their model, and I got really excited, and I was like, I want to come work for Quilt. I want to come bring these ideas and these practices from large companies to the broader community and to open source. So what does it mean to manage data like code? Well, in software engineering, we take for granted things like version control, having clean, explicit definitions and interfaces between your modules, having unit integration tests, having standard observability practices like logging and metrics and tracing. And so we want to bring all those equivalent notions to data sets. So it seems very intuitive that we should version our data set so that we can reference it, roll back to it, audit it. We should have clean and explicit interfaces between the code and the data. And what I mean by that is we should have very explicit definitions of all the data that goes into a pipeline. So that should be the input to your data pipeline. You shouldn't be loading side artifacts because those will make it hard to audit things. And they'll also introduce bugs as you go and extend your pipeline. We want to have data quality checks and schema checks that run automatically, just like unit tests and integration tests, so that you can ensure the different subsystems of your database and your pipeline are making the same underlying assumptions about the data. And then you want to monitor the data sets for regression. So you want to look at things like what's the standard deviation of a column, what's the range, what are the mins, the maxes, and be able to alert and potentially run a circuit breaker in your pipeline. So if you're seeing bad data halfway through, you can stop and save yourself some CPU cycles. There we go. So to motivate this talk, I want to talk about an example pipeline that I built with our developer advocate, Alexi. And we built this a couple weeks ago at a Civic Tech Hackathon. And it starts out as a kind of a good toy problem, so it's easy to understand. But it will, as the architecture evolves, it will display a bunch of these problems that we encounter and that I've seen before at real systems like at Sidewalk Labs. Okay, so what we set out to do on that Saturday was we wanted to build a database of historic bus delays in the New York City Metropolitan Transit Agency. And the way we decided to do that is we were going to go out and we were going to scrape the GTVS RT feeds for buses. So we would get live updates of where all the buses in the system are. Those produce protocol buffer results that we would dump into blob storage. And then we're going to run a lightweight Airflow ETL that will take those protocol buffers, compare them to the static GTFS schedule, see what buses are delayed, see how far they're delayed, label that data, and then dump a serialized data frame every day that would give us a set of data that we could then take to a machine learning model and train so that we could predict when are we going to see bus delays and what are the likelihoods. So it immediately became clear that there was a lot of data out there that we could use to augment our data, or our labeled data, to get a better trained model. So we wanted to incorporate that into our ETL pipeline. So we were able to, for instance, go out to weather.gov and find historical weather data, add that to our system, because that seems like a pretty good feature if we wanted to detect bus delays. We were also able to go out and go get surface level congestion. So companies like Here and Uber Movement will provide transit, or not transit delay, but driving delays in different cities. So we were able to go out there and get that. Unfortunately, it's in an OSM format and not GTFS. So we have to set up another ETL pipeline that will take that OSM file, join on GTFS, and tell us what the congestion along the route is, so that we can then add that to our label training data. So pretty quickly, our pipeline's getting complicated. We have a lot of new data sources. We have 2 sub-pipelines now because we have to do this joiner to get the congestion data. And then if that wasn't worse, we found that actually the GTFS RT feeds don't cover all the bus routes. So we had to go out and find another provider of real-time bus data who provides it in JSON. So we dump that into another bucket, add more logic to our ETL to join that in. And now we have this full pipeline that will produce our data to go into the first phase of training a model. So what kind of problems did we encounter in this system? Well, we found incorrect schemas all over. Different agencies and different routes would have different GTFS files. Some of them didn't conform to the standard. They'd be missing core pieces, like the stops file, that would break our adjoining ETL pipelines. We found misaligned and bad time zones everywhere. Some of the data sources use local timestamps. Some of them use timestamps without time zones, some with. Some use UTC, so we had to be very careful in our pipelines about being aware of what was what. We found timestamp mismatches. So the GTFS schedules are static files. They're valid for about 7 days. If our pipeline ran for more than 7 days, the real-time feeds would no longer correspond to a schedule. The routes could potentially have changed, so everything would get labeled as being delayed. We found missing data issues, so if our scrapers timed out or backed off, that would ripple through our pipeline. And then we also had underlying issues with, we had these two sub-pipelines now. They both had a shared dependence on the static GTFS file, but we had no requirement that those were the same GTFS file. And so sometimes we would have issues where the congestion data for a route would be totally out of sync with the actual routes that we were computing. So how do we go about enforcing data consistency so that we can avoid these problems, so that all our data is referring to the same time range, and also that our underlying data sets are consistent to the different pipelines? All right, here we go. So if we think back to the pipeline for a minute, we saw there were those two phases of the pipeline that both referred to GTFS. If we were thinking about this as just normal code, we would immediately see that as a code smell, and we would think, don't repeat yourself. Why am I including the same data set in two different places? Why aren't I referring to this as just one single object? And then the other thing that we could think about is how do we make sure that all these individual data sets have the same date time range? And then the really important thing is whatever tool we use to enforce this consistency, we're going to want to lift that up and bring it to the serving side of our machine learning pipeline when we're done. So we're here just having issues enforcing consistency only on the labeling side. But whatever we do, we want to be able to bring that so that our feature set on serving time is also consistent to avoid this training serving skew issue. So this was the diagram of the pipeline. We see the GTFS schedules as they're a dependency that appears in multiple places. And really what we want to do is we want to kind of grab all the data that exists on the edge of our system. And we want to find a way that we can refer to this as one consistent unit. So here it's the GTFS files, it's the OSM congestion, the weather, the raw feeds that have been dumped to BLOS storage. And we're going to call this unit a package. So now we want to operate on the data as a single global package, and that'll remove a lot of our issues. So what do we need to have a good usable package definition? Well, we want to have a global singleton for the data so that every subsystem ends up referring to the same underlying data object if it's supposed to be semantically the same. We want to make sure that it's immutable and that it's reproducible. So if I want to run my pipeline later, I'm guaranteed to be able to run it on that same data, and that data hasn't changed. We want to make sure it's versioned so we can compare different runs. And we'd really like to make sure that it's language agnostic. So if different parts of my pipeline are written in different languages, if I have different microservices, they can all lean on this same shared standard. So this is what we came up with at Quilt. It's a very lightweight definition that we call package manifest. And what this is a JSON-L file, which means that each line is a JSON object. The first line describes the package. It has some high-level information about the version, a description of it. But the main meat of the project is it's a series of entries that are pairs of keys. So there's a logical key, which is the way you'll refer to your data object. So in this case, it might be a GTFS file. And then there's a physical key that points to its location, in this case in S3, and in S3 in a versioned fashion. So we're guaranteed that when that object is updated, this package manifest still points to that original version that was used in my pipeline run. And then additionally, we include some information like size, hash, so we can check the data consistency, and some user-defined metadata that we'll find is very useful later. So once we have this manifest, instead of each phase in the ETL pipeline taking its own input, it can read the manifest and then read its files from that manifest. So here, these two ETLs, they accept the manifest as input. They both read the same underlying GTFS structure. They're guaranteed to be consistent. And that helps remove that kind of skew issue we were talking about for GTFS. Similarly, we can add the time range as metadata to the top level package. So each phase of the pipeline can compare the underlying data that it's reading to the high level package time range, and it can ensure that its data set conforms to the time range we care about. So what is the life cycle of a package? It's a lot like Docker. You build your package, you publish your package, someone comes along and installs your package. And so at Quilt, it's this notion of build, release, run. You've probably seen this in the 12-factor app. But it's a way of distinguishing the phases of the package lifecycle. And we have a command line interface and a Python SDK that makes this easy to use. And this is really well suited for batch style jobs that are ingesting their data from a data lake. It does not apply as well to a streaming or continuous framework. Okay, so once we have these packages, how do we go about versioning them and comparing the versions of that data? So you're probably thinking, hey, I already have a way for versioning my source code. Why don't I just put my data in there? I could put it right. I can put all my CSVs in GitHub, and then I don't have to worry about tracking them and comparing them. Well, the problem is that doesn't really work. GitHub has poor support for large files. Anytime you have a file over 100 megs, you can't put in GitHub. The repo size blows up. It increases in proportion to the number of updates on your file and not the size of the files. So you can very quickly get massive repos that are going to slow down your development team. And the diff algorithms are based upon new lines, so they're not suited for binary file formats. So we want something that's going to give us the features of GitHub, but is really tailored towards data. So the observation that we had was, hey, S3 blob storage, it has all these properties we care about that are really useful. It's got versioning at the object level. It's got high availability. It's got high throughput. The problem with it is it's not designed to be easy to use to manage a set of cohesive data. It's not designed to be browsable. It doesn't have a good user interface. So what we did is we built a data collaboration layer that lives on top of S3 that abstracts out those ideas for you so you can interact with your data set as a whole, but underlying it's using all this technology. There we go. And then the great thing about versioning packages is they're a very necessary component of having a reproducible machine learning pipeline. It's not enough just to say that, hey, I have my code in GitHub, so I know I can rerun my pipeline. You need to know what was the data that went into your pipeline. You also need to know what are the artifacts on your model, what are the parameters, what are the hyperparameters. So if you combine the versioning from these things, from your code, from your data, and from your model, then you can have a cohesive view of what's going on, and you can go and reproduce your experiment. The other thing that versioning packages gives you is you can use the metadata at the package level to track data lineage. So if all of your ETL pipelines consume packages and produce data from them, they can tag that data with the packages that was used to produce them. So if you want to go do an audit, you can do a search on all the data that was produced by package X. You can use it to run comparisons between different versions of the data set. So if you have a snapshot for every day, you can run the same Python notebook on each snapshot and compare them. And you can use them to skip already computed phases in a pipeline. So if your pipeline is trying to compute a property of package X and it sees that it already has an output that was produced by X for the same code hash, it knows that it can skip this phase. The next thing that I want to talk about is how do you go about documenting your data sets? Nobody would question that you have to document your code. So how should we document data sets in a way that makes them easy to use and discoverable? So I'm going to do a quick example. The Wi-Fi works? Yes, great. So this is a data package that was written by Rob Newell. It's kind of a small toy example that compares US poverty rate to smoking data and then joins that with the US Census Bureau track so you can kind of explore it. So up here, you can browse the logical keys in the package just like you would be browsing an S3 bucket. You can click around, explore them. You can write a README file, and just like GitHub, it will render that markdown in the browser so you can explore it and read about where the data sources are coming from, get a high-level description. You can embed Vega visualizations that refer to properties in the package. So here is a live example of the smoking incidence rates per county in the US. And the great thing about this is that if you change the package, the visualization will change with it. And then last, and what I think is actually most important, is that when you package your data set up, you should include examples of how to consume it. So here is included an analysis of the data set so that anyone else who comes along and says, hey, I want to use the smoking data set, will see this Python notebook, they'll see what the data frame looks like, they'll see the column objects, and they'll get an idea of how to immediately operate on it. And so here we render the Python notebook inline. And then I just want to show a quick example of, so these are the Vega visualizations. So here's a correlation between poverty and smoking. And the really cool thing about this browser with versioning, you can go click and you can say, hey, I want to explore what this visualization looked like in a different version of the package. And that will let you kind of do a comparison and see if there was a regression. And then the real question is, how do I get out of here? Thanks. Thank you. The other thing that is really great is that we can use those metadata, the metadata facets on the objects to apply tons of information as a JSON blob. And then in our browser, we allow a search functionality. So just like everyone else, it's backed by Elasticsearch. And what you can do, so here's a great example. If I tag all my Python notebooks with the package and the version of the package that I use to do the analysis, I as a user can come to the browser, I can search for user metadata.built using package and the property I care about, and then I get a whole set of results that's everything in my bucket or everything in my set of packages that was derived from that data. We also support a lot of, we talked about Markdown and we talked about Python notebooks. We support discoverability for a lot of other things. Here's an example of inline images that are rendered. So if you have a large data set that involves images, you can scroll through the browser and see the thumbnails very quickly and identify if there's something that you care about before downloading the whole thing. And here we have, this is an example of a Parquet file that we render in the browser as a preview for you. We select, I think, 50 rows randomly that we render for you. You can see the columns. I'm not going to go into the demo because I don't know how to get out. But if you go into the demo, you can see that you can actually click in and you can explore the schema and get a real-time observation of what the schema is for your Parquet files. So next I want to talk about schema mismatches that occur not just within an individual file like Parquet, but across your system and across your package as a whole. So let's say that we've got our pipeline up and running. We're really happy with it. It's producing historical data for New York. Now we're like, hey, these are all open standards. We should be able to pick this pipeline up and just drop it into San Francisco and everything should just work, right? That'd be great. Well, here's the problem. Unfortunately, we couldn't find any congestion data for San Francisco. We were only able to get it for New York. So that's kind of a bummer. And oh no, our pipeline really counted on that data being there, so much so that it failed. And so then it failed to produce this other data. And so then the last pipeline failed. And that is really a downer. But even worse is, what if my pipeline didn't fail and it just made some wrong default assumptions, and now it made garbage data that propagated up and was joined, and now we just have garbage data in our labeled data set. So really what I want to know is, when I go to pick my package up and define it for a new city, I want to make sure that everything that's necessary exists in the new city before I run an expensive pipeline and I get garbage data. So we have this idea of a package schema that is just a very lightweight You add as an entry to the first line to the to the package definition that the package is going to implement a schema. We version schemas as well. And all this does is that when we validate the package, we guarantee that every logical key that's defined in the schema that it implements must exist in the underlying package. So now you know when you go to make San Francisco, you're like, hey, I assembled all of my data. I'm ready to run my pipeline. Before you even do it, when you go to publish your package, it'll say, wait a minute, you're missing your congestion file. And so this is still a feature that's in progress that we've been working on. We've been playing around with the idea of whether we should allow default fields or not. That's something that we're curious to see what people's opinions are. And then the last thing I want to talk about is how do you catch bad data early? So we want to catch schema and data quality issues before we run a pipeline. At Sidewalk Labs, a lot of our pipelines regularly cost in the thousands to even tens of thousands of dollars to do a run. So they're very expensive. If you have bad data, it's a huge bummer. So we want to make sure that we know before we start a pipeline that we can run it and that we shouldn't just fail. We also want to decrease the time that's spent debugging data quality issues. Even if your pipelines aren't that expensive, the amount it takes to pay a software engineer to figure out why your data is bad is a lot. So we would like to avoid that. And then finally, we want to decrease the time that you take in your cycles between getting data from your outside providers. If you've ever worked with city agencies, it takes a really long time. It's very expensive. People bill these hours, and then they give you data, and it's missing columns, and it has mislabeled things, and you go back to them, and it's another 2 weeks. So we want to break this cycle so that you know as soon as you get your data, you have everything you need. So we have this very lightweight annotation that we use to extend Python unit tests. And it's a way of referring to the logical keys in the manifest, and it lets you write some lightweight validation logic. So here's an example for the GTFS file where we said, hey, I want to make sure that everything in my manifest that says it's a GTFS file actually is a real zip file, and that it actually does contain the stops file when I unzip it. And this is something that's very much like a unit test. It's like enforcing the schema. You can use it to enforce the types. You can use it to enforce the ranges. You can say, hey, I want to make sure everything in this column is actually between 0 and 100 and not like a nan. And then we can also use it to implement things that are like integration tests. We talked before about putting the date in the package level manifest. And so you could use the same thing. So you could say, hey, I want to make sure that all my data sets, all my individual data objects fall in that same range by writing a similar unit test. And then we can use things like this to do run a small sample, for instance, like a 0.1% run to validate your pipeline in a staging environment. And we can implement a CI stack so that when you go to publish your data, first it'll stage it and then it will run the tests, and only once the tests have passed will it publish them. And that way anyone who wants to consume your package can have some level of confidence that the data is valid. And so this is actually a pretty tricky problem. Processing data is not really what Circle CI was meant for. The containers are too small. It's actually really slow. It's super expensive to chunk through terabytes of data. So we've been working on building some systems where we use larger containers and we do it less frequently. But in general, this is the type of problem we're trying to tackle. So I just wanted to end with some of the ideas that we have for best practices for data set management. These are kind of like the 12-factor app best practices, but applied to data. So we care a lot about making sure our data sets are versioned. We care about making sure they're immutable so they don't change. We care about them being reproducible. We care about them being documented, interchangeable so that I can pick up my pipeline and move it to a different data set and it will still run. So if I have an image classifier, I want to be able to say like, hey, I want to run this same code on a different set of images and labels, and it should just work. We want to be really explicit about our data dependencies so that data is not coming in a sidecar or in a side channel artifact. We want to make sure that it's portable, that it's extensible so you can add things to your data set, and that it adheres to this build, release, run idea. And we think that these are all properties that are really important to think about when you're trying to manage your data sets, but our hope is that the tools we're building will let you not have to think about them in the future. So please reach out to us. We're on GitHub, we're on Twitter, and we're also hiring a cloud engineer in San Francisco. So if that interests you and you want to come build tools with us, find me after the talk. Any questions? Oh, sorry, say that again?
If the schema didn't change, how do you manage the dependency of the different versions of package?
So his question was, if the schema doesn't change, how do you manage the dependency between versions of the package? So when you publish the package, you give it a name and a user space. So we track that in the repository. We have it in GitHub. I think it is not published yet. We'll work on that. Alexei, who couldn't be here today, is plugging away at it. Thanks. Okay, I think that's it. Thank you, everyone.